Hello, my name is Steve Akers, and I'd like to welcome you back to the Boston University Metropolitan College lecture series on the topic of blockchain. In this last of the 3 lectures on blockchain, I'd like to compare and contrast the Ethereum and the Bitcoin public ledgers and explain the concept of smart contracts, and then look forward to some scaling initiatives that are in place for Ethereum and Bitcoin in the future. Again, this is blockchain for everyone. We don't need to be cryptographers to handle this. In both the Bitcoin network and the Ethereum network, we're still building a transparent, immutable public ledger that exchanges value between parties. There's still wallets generating transactions and having them written down immutably in the public ledger. Where Bitcoin was designed as fundamentally a cryptocurrency platform for exchanging bits of cryptocurrency between entities, Ethereum has a very different mission. They've taken on the very aggressive goal of becoming the world's computer. So they have a public ledger, but they want to build computer programs on top of it called smart contracts. So with Ethereum, they have their own Ethereum Virtual Machine, just like you'd have with a Java virtual machine, that allows you to build any kind of program you'd like. And they have a programming language, and the language is Turing complete. As we learned in lecture 2 on Bitcoin, the Bitcoin developers selected a very limited validation language called stack-based script. And script limits the amount of instructions that one can execute on the network to validate transactions. So it's Turing incomplete. It doesn't allow you to loop and branch and jump and do all the things you can do with a general programming language. And they did that by design, as we'll remember from lecture 2, because they wanted to protect the network from denial of service attacks. They didn't want a programmer to make a mistake or have a nefarious attacker inject an infinite loop into the Bitcoin network and deny service to everyone. With Ethereum, it's very different because of this Turing complete language. They had to figure out how to protect themselves from letting the network go into an infinite loop and deny service to everyone. So what they did is they introduced the concept of fuel. So in Bitcoin, as you recall, transaction fees are implicit. With Ethereum, what one has to do is buy fuel paid for in units of gas purchased with Ethereum. So when one runs a transaction on the Ethereum network, one has to pay for it with certain increments of gas or fuel. If a developer put a bug into the code of their transaction or their smart contract, as we'll see, if they paid a certain amount of gas, when that's used up, if they went into an infinite loop, the program would stop running, and the network would therefore not run out of control and have a denial of service attack. So this concept of gas and fuel permeates how the blockchain works, the amount of time it takes to mine a block, the number of blocks per minute. Smart contracts also use storage as well as instruction compute time, and there's a transaction fee itself. So all that goes into a complex calculation to determine how fast a block gets mined on the network. So this concept of gas changes everything. Before we get into all that, let's look at the Ethereum ledger components. So it looks pretty much like a Bitcoin network with some differences. So there's still wallets. The wallets speak to full nodes. The full nodes are implemented in the network on a cooperating series of computers that obey, and the software obeys strict consensus rules, so there's no central authority. It's still trustless. The goal is to build the longest blockchain, bundle up our transactions, put them into a block, mine them, and create a longer and longer blockchain. One big difference is in addressing. So when one creates a new wallet on the network, one gives it an address once. So one does not have to generate an address per transaction like they do in the Bitcoin network. The other thing is, you'll notice there's no mining layer in this network. So whereas in Bitcoin there are specific nodes which have hardware attached to them, the Ethereum developers didn't want that to occur because they didn't want the hash power to be centralized in the hands of a government or a single company, even though it's a trustless blockchain. So they picked a different hashing algorithm called ETH-hash, which needs to go outside of the CPU into memory, walk a tree, And that isn't conducive. It doesn't lend itself well to having one single semiconductor just generate hashes like a SHA-256 does in Bitcoin. So they picked a hash algorithm to discourage hardware mining. Miners get around that by using these NVIDIA mining cards that you play video games with to compute the ETH hash algorithms and accelerate things. But still, it isn't the same as having vast farms with just ASICs that compute these hashes on behalf of the Bitcoin network. The other major difference is Ethereum has a shorter block time due to this gas concept. Because of the shorter block time, there's a higher incidence of blocks arriving out of order or at different times. So instead of having an orphaned block outside the longest part of the blockchain that never gets a mining reward and is never referenced, the Ethereum developers allowed blocks outside the main chain to be referenced. They're called uncle blocks, and they're given a partial reward to the miner by the network if they've mined a uncle block. So it's a different concept. The rewards are distributed a little differently, but these short off-block chains are allowed. Ethereum does not use the unspent transaction output model. Because you have one wallet address, the wallet just keeps an account on its own of what ether or currency it maintains on the network. Because there's only one wallet address and you're not going to generate an address for each transaction, you don't need this unspent transaction output model. So you don't need to spend, as we saw in lecture 1 and lecture 2, a whole Bitcoin and send a bit of it to Alice the barista and back to yourself as change. So that's one big difference. So transactions go and there's a credit debit balance on your wallet account. They call it an account. Ethereum tokens are issued in constant sequence. With Bitcoin, there are going to be 21 million of them mined, and that's the hard upper limit. So the value of Bitcoin is going to go up when we've mined all 21 million because the supply of Bitcoin entering the network will go down. So the theory is it's going to be more valuable. So the Bitcoin network will live off transaction fees at that point. Ethereum has no hard upper limit on the amount of tokens or ether that'll be mined. The miner of an Ethereum block gets 2 ETH at this point in time and 1.75 ETH for mining an uncle block, one of the blocks off the short part of the chain. The Ethereum block time is shorter, so you get a block every 14 seconds on average with Ethereum. And that's due to the fact that a miner can only earn 1,500,000 units of gas for mining a block. The average transaction complexity, as they call it, of a transaction in the Ether network is 21,000 gas. So you divide the average transaction complexity into 1,500,000, and you get 70 transactions per block. So Bitcoin, as you recall, has about 1,500 to 2,000 some transactions per block. One comes out every 10 minutes. With Ethereum, they have approximately a block coming out every 14 seconds. And the number of transactions per hour varies because you're spending some of this gas in the block on smart contracts, which we'll look at next, as well as just straight transaction fees, as well as storage of data on the Ethereum public ledger. So this concept of gas, this is what I was saying, it permeates everything and changes the velocity at which transactions pop out of the Ethereum network. To give you some perspective on this, a Bitcoin network, depending on the amount of transactions in the block, will have about 3.3 to 7 transactions per second. It's not a lot. Ethereum will have around 13 to 15 transactions per second. You can Google this and go see the current Ether transaction per second rate. And that's, again, because you can't nail the Ethereum transaction per second rate very succinctly because it's doing a lot more things, as you'll see in a minute. Addressing, as I said, is different. Bitcoin uses a different address for every transaction. Ethereum has 2 kinds of addresses. So your wallet address, a person instantiating a wallet and sending ether from one wallet to another, that's called an externally owned account. That has a public and a private key. One can generate a new contract on the network with an externally owned address from their wallet and create a piece of code that gets mined into the blockchain and run, so it has to have an address. So that has a contract account address. So because we can create these contracts, send them up to the network, and put them in the blockchain, we have to be able to address them. So we have an externally owned account with a full public-private key pair for exchanging value and starting up smart contracts. We have a contract address, which allows us to address a contract. And the contract address does not contain a private key. So a contract, a smart contract, which is started up and run on the network, it cannot create transactions on its own because it doesn't have a private key. An Ethereum transaction has a nonce, it has a sender and a receiver, and a nonce allows the sender address and a certain value to make that transaction unique so you can't replay the transaction on the network. There's a gas price. The gas price goes up and down. There's a call your wallet makes to figure out what the current reasonable gas price is. There's a gas limit, the amount you're willing to spend. So on average, 21,000 gas for a transaction. There's a recipient, the address you're sending it to. So if I'm just sending Ether to another address, then I'm just gonna call the recipient an endpoint, an externally owned address. I'm just gonna say the recipient is this other externally owned address with a public-private key just like mine. The transaction also has a value. The value field is the amount of Ether I'm sending. So in a regular transaction, which is my address to another address, I'm sending a certain amount of Ether to another wallet or to a smart contract. Data can be sent along in this message of a transaction. That's how I get the code up to the network to have it mined in a block to be run later in a smart contract. And then, of course, this has a digital signature like any transaction in Bitcoin or Ethereum. Smart contract, the way it would get on the network, we have the regular public ledger with the full nodes. But remember, we have an Ethereum Virtual Machine, which is capable of pulling these smart contracts up off the network, putting them in memory and running them like programs. Every node in the network, it's important to note, runs that same contract all at once. They all get an answer, and the answer is supposed to always be the same. And when it is, one of them is going to get to write it in a block, and it's going to be mined into the blockchain with the results of the smart contract execution. To get it up there, we use what's called IDE, an integrated development environment, like you'd use to write programs of any kind. And you write your code in Solidity. For example, if we wanted to build an ATM machine that's a smart contract on the network, so I can build the code in my IDE. I can type in the functions for a deposit, a withdrawal, a transfer from one account to another, one address to another. And I can compile that in this integrated development environment with the Solidity compiler. And I can create a transaction which sends it up to a special address on the Ethereum network called a contract creation address. When I invoke that transaction with the data field of that transaction I just showed you, containing the bytecode I've just compiled, what that does is that creates a contract, sends you back an address, and it compiles that code at that address into a block on the blockchain. After I do all that, then for my ATM machine example, what I can do is I can fund the contract. I can send it some Ether that it can dispense to qualified recipients. I can write the code such that several people at my company are authorized to use that contract. So I, as the manager, could fund the contract, and as I approved expense reports, I could let my employees withdraw the amount in Ether to their wallets that reimburse them for their expenses. So I fund the contract by depositing 5 Ether to it, and then I can withdraw it back to my wallet or let them withdraw it to theirs. So that's kind of what a smart contract is and does. The results of that is the balances change. So if I put 5 Ether in, and I allow people to withdraw 1 and 2 and 3 Ether, those balances for each of our addresses change, and that gets written back to the blockchain. That's called storage. So I have to pay for the transactions to fund the contract and allow people to withdraw it and to pay for this storage. So remember, again, that these are very much computer programs, and they're going to run, and every transaction that I invoke is going to cost some Ether, and in the form of buying gas to fund the operation and the calling of the contract. This is some actual code which I would write, and I know it's code and that this is a general presentation for non-computer scientists, but this is pretty easy to follow. So at the top of this code, I say, here, give me a storage location that is going to contain the balances. That's all fine and dandy. So I'm going to have a slot in that storage location for each person who calls it. And then I'm going to have a deposit function, which increments my balance. I'm going to have a withdraw function, which takes the sending address of the entity, the EOA calling the contract, and I'm going to update their balance and decrement the wallet balance. And then I'm going to be able to transfer between parties. So I implement these functions to deposit, withdraw, and transfer funds. So now it's like an ATM machine. So it's really not that hard to understand. It's not that complex. And the smart contract on the network will update these balances, check for insufficient funds, and only allow the transaction to succeed if there are sufficient funds and the person's authorized to use the ATM machine back to their wallet. So you can kind of get a feel for how these things work. One thing to remember about this is that sometimes what one might want to do is go off the network and pull data into the blockchain for a smart contract to operate on. So we have a trusted entity outside the Ethereum network called an oracle. So oracle, like the Oracle of Delphi, where you'd go and the oracle would speak to the gods, the outside world. They have defined an oracle component which can go out, access your bank, for example, access the company bank account, draw money, and then convert that to Ether on the network to pay the expense reports. So this back and forth with the real world in a piece of code you write to talk to an Ethereum wallet to convert dollars into Ethereum is done by an oracle. One thing to keep in mind is that smart contracts, as we'll see in a couple slides, they work best if they're dealing with Ethereum-based monetary currency on the public ledger. They don't work really well when the data is off the ledger and you can't rely on it. So smart contracts run on the ledger. They should be dealing with data that only exists on the ledger. Finer points of these include, remember that contracts don't have a private key and they can't create their own transactions. So you need to write your code so that you create transactions to the smart contract and it moves things for you, but it only happens because of you invoking them with a transaction. The other thing is, if you have developers using these, if they want to maintain a lot of state, a lot of bank balances, they have counters and things like that, those have to be stored on the blockchain when the results are mined. So that storage costs quite a bit of Ether. If I had a bunch of developers writing smart contracts, I'd watch them carefully that they didn't write their code in such a way that we're storing so many things and incurring such a cost in Ether that it's not worth having them on the network in the first place. So there are tricks to this. It's like any new technology. People get excited about it and they start writing these smart contracts, but there are costs to running these, and you got to be careful as to how you let your team write code in smart contracts, because you could go broke. One interesting aspect of smart contracts is there's a standard called ERC20. It stands for Ethereum Request for Comments, where you can generate your own kind of token. So instead of just exchanging Ether, you can write smart contracts that create and exchange your own money, basically. You can create your own coins, and you can use those as currency within your own application. So the trick here is you have to make sure all your smart contracts know what kind of standards you followed, and you have to use the right naming conventions. Then you can define your own token. So I'm going to show you an example of a virtual casino where we exchange dollars for virtual casino chips, poker chips. And those are our own coins. We're exchanging them among ourselves, players of the game, and they represent value. You have to be careful, though, because in the early days of this, people were sending contract tokens to addresses at regular exchanges that accept Ethereum. And if you send these to a smart contract that only knows about Ethereum, you've just burned your contract tokens. They can't be just sent anywhere. So You have to write code specifically and have wallets that specifically understand your kind of token, or you run the risk of sending them somewhere that they're lost forever. A lot of the altcoins are implemented on top of this ERC20 token infrastructure, where they're actually using the Ethereum protocol to handle their own tokens that are strictly for cryptocurrency purposes. So there are companies that use these. They issue them to their company employees as value, and they even set up smart contracts that handle the vesting. So if you have a startup and you vest so many shares in your company to employees over 4 years, you could do the same thing with these ICO tokens and give them 25% of their vesting over 4 years by having a smart contract check their employment validity and then move some of these special tokens which have value to the employee's individual account, so it can handle vesting schedules for you. It's kind of interesting. Okay, so here's my virtual casino. So I go out and I contact the game, which obviously runs outside of this. It'll contact wallets to move things inside the network. I authorize my bank to move money to the virtual casino bank account, and the Oracle converts that with the help of a component in the game into virtual poker chip tokens. So I buy $1,000 worth of $100 poker chips. I get 10 poker chips. I go into the window of the game where I'm playing blackjack with the dealer. If I win, the dealer pays me a couple poker chips or blackjack chips. If they win, it goes from my wallet back the other way, and this is all managed by smart contracts. So these transactions are being invoked by the game, and we're exchanging value in our own token to fund this game. If I go bust, I have to go back outside the game and have the Oracle put more value on the public blockchain under this contract. You know, as I said, people get excited when they start seeing a new technology and they say these smart contracts would be great to update my bank balance by paying my utility bill for me or something. The only problem with that is, remember, the smart contract's going to run everywhere in the network. So you'd have to write a very complex smart contract to coordinate among all the instances that would run to call your bank balance once. It'd be fine to read your bank balance if only one of them would call back out and spend the money. And coordinating all that is very hard. So having that data in your bank balance that you're relying on off the chain is a bad idea. If you could bring a value in, so say you had a derivative swap that you wanted to execute based on the price of a market basket of bonds at a certain time on a certain date, you could bring that information inside the blockchain, invoke a smart contract, and have the contract fulfilled by swapping ether between parties. As long as you can lock the data on the blockchain, then this smart contract paradigm works well. It's just when you're relying on data outside the blockchain, those use cases probably won't work. Okay, so now that we've talked about Ethereum and smart contracts, let's talk about blockchain in general and some of the scaling initiatives. The reason we need scaling initiatives are that right now, Bitcoin and Ethereum are seen as basically stores of value, like gold bullion stored in a safe deposit box. You can't transact very quickly with them. The Bitcoin 10-minute per block time is kind of onerous. Ethereum isn't much faster. So to get up to where Visa processes 45,000 transactions per second or something of that nature, we have to do something radical. We have to have another layer in the protocol. So we've developed something called the Lightning Network. There are other initiatives other than Lightning Network, but I'll explain this one. It is a layer 2 protocol in that it rides on top of the blockchain. So two people decide they want to open a secure payment channel between themselves, and they open a multi-signature wallet. As we learned in lecture 2, a multi-signature wallet requires 2 or more signatures to validate the transactions on the network. So by opening this multi-signature wallet, Bob and Alice secure the channel between themselves with well-known cryptographic approaches. Then they fund the multi-signature wallet with a Bitcoin each. And then what they're going to do in this secure channel, without waiting for the transactions to be, the microtransactions, to be written to the blockchain, they're going to write them to this multi-signature wallet, and the microtransactions are going to be handled at the layer 2 level. So we'll keep a balance sheet of the micropayments flying back and forth between Bob and Alice, which can happen much faster than they ever could if they were mined individually on the Bitcoin or Ethereum network. So at the beginning of this, when Bob and Alice commit their single Bitcoin each to the multi-signature wallet, that's the commitment transaction. That's written to the blockchain. So we know they opened this wallet and each has a Bitcoin in the wallet. Then back and forth at the Lightning Network layer, they're committing half a Bitcoin in one direction, half a Bitcoin in the other, quarter Bitcoin Bob to Alice, etc. These micropayments are written down in a ledger in the multi-signature wallet, the Lightning Network layer, and they're justified later. So when Bob and Alice tear down the channel, either a certain amount of time expires and the channel expires, or they decide to tear it down, then the balance sheet, the individual balance owed Bob and Alice, is written in what's called a fulfillment transaction from the multi-signature wallet. The Lightning layer has them both sign it, and that's committed as a fulfillment transaction to the Bitcoin network. Therefore, there's the beginning and the end, and the balances end up in the fulfillment transaction. So in the beginning, we had a Bitcoin each in Bob and Alice's control, and at the end, we might have 1.5 Bitcoin in Alice's wallet on the real blockchain, and a half for Bob, because several payments were exchanged and services rendered inside this micro wallet layer. So this has the potential of allowing us to get up to transaction values that rival Visa or MasterCard. And this could be a very promising development for general retail use of Bitcoin. This is in the nascent stages, and there's still a lot of testing to be done, and there are several security issues to be worked out, which are far beyond the reach of this presentation in the time we have. But this is a very promising layer 2 protocol we could use for speeding up Bitcoin payments. There's also an issue with using exchanges. I'm sure we've all read about certain exchanges being hacked. So an exchange for cryptocurrency is one like Coinbase, Bitstamp, etc., where when Bob wants to buy a Bitcoin, he opens an account at Coinbase, he has an application on his phone, it contains a wallet. He authorizes his bank to pay Coinbase's bank X amount of dollars. He buys a Bitcoin in the app. It gets transferred to a wallet owned by the exchange on Bob's behalf, so it's a proxy wallet. While Bob has that Bitcoin out there, he has to trust the exchange to secure his funds. He can always move those to his wallet, but they're at the exchange temporarily. Alice does the same thing if she needs to buy Ether for some reason. A hacker could conceptually hack the exchange and pull those Bitcoins out, and Bob and Alice would be out of luck if they haven't latched them down to their own private wallets. So the way around this is being worked on by several companies. One of them is a local company, and the founders are from BU. One is a tenured professor from BU. But it works on the principle of atomic swaps, where Bob and Alice can exchange Bitcoin for Ether and never go to an exchange. And that's, again, a layer 2 protocol, so there's a swap software layer. And if Alice wants to initiate an exchange with Bob, what she does is she says, great, I agree on this price, what do you think, Bob? They agree off-chain here to exchange 1 ETH for 0.03 Bitcoin. Alice generates a secret value like a public key. She hashes it. And she locks down on the Ether blockchain 1 ETH, and she locks it down with that specific hash. Bob, in his swap layer in the software, he uses the same hash, and he locks down 0.03 Bitcoin on the Bitcoin chain through the swap layer. Alice is committed to leave that chain open for Bob for 48 hours. If Bob claims that within 48 hours, he gets the Ether. If not, the swap layer sends it back to Alice. If Alice claims her Bitcoin from Bob, what she has to do, since she locked her Ether with a hash, she has to supply that hash, because Bob used the same one on the Bitcoin network. And what she's going to do is she's going to reveal that public key that she used to create her lock that Bob has to unlock later. Once she's done that, once she's revealed the secret, the public key, and unlocked Bob's Bitcoin, Bob can go in, he has that secret, and he can unlock her Ether and move it to his wallet. So they've essentially swapped Bitcoin and Ether on their respective blockchains, and there's no exchange involved. The reason Alice has to lock her transaction for 48 hours and Bob has to lock his for 24 is Alice could wait till 23 hours and 59 minutes and unlock her Bitcoin if she was nefarious, and that wouldn't leave Bob enough time to unlock his Ether and get paid. So by starting the transaction, she has to agree to lock her transaction longer, give Bob more time to grab his transaction before her refund. Bob has a shorter amount of time, and once she produces her secret, Bob can unlock his Ether, and he has to do that within 24 hours. So that's an exchangeless atomic swap, and it's a pretty cool idea. There's a company called Arwen. You can find them at arwen.io. It was started by a BU professor, Cheryl Goldberg. I don't know her, but I've seen her content. She's very smart. And they're working on this exchangeless decentralized ledger. So they use this atomic swap concept, and that's very exciting because if you had a public ledger with a decentralized exchange, you wouldn't have to pay the fees, and it would be much more secure. So that's something to keep our eyes on as we look toward the future of these applications. If we didn't have to worry about being hacked in an exchange, and we could transact more easily in a decentralized manner, that sort of sets the world on its ear. I mentioned earlier there are a lot of billionaires committed to Bitcoin based on their view that it's just a good store of value. So where Paul Tudor Jones, famous hedge fund manager, Mark Lazary, another hedge fund manager, is they've committed like major percentages of their net worth, 2% in Paul Tudor Jones' case. He just commented on this a few months ago at CNBC. He really sees Bitcoin as an asset class that's worthy of tying up his net worth much as he would in gold to hedge his portfolio. So along come these payment initiatives like the Lightning Network that turn it into a true currency, and that could be a very good bet. So there's several billionaires and venture capitalists who've bought a whole bunch of Bitcoin under this premise that if we just wait long enough, which is only 2 or 3 years, Bitcoin will be very, very valuable. Looming issues. There's some looming issues in the network. So those of us who look at the world of computing, there are these new machines called quantum computers that work at exponentially higher rates than present machines that we have today, standard computers. These can theoretically crack public-private key cryptography. These are mostly lab machines at this point. We don't really have working, robust quantum computers. But if we had these in quantity and they were ubiquitous, you could theoretically rewrite the blockchain. And if that happened, we'd have a problem knowing what transactions were really valid or not. Now, the other way to look at this is when you have this kind of technology, it's sort of the race of good versus evil. With quantum cryptography, you could also use it to rewrite the blockchain with new algorithms that are less crackable by quantum computers. There are people at BU working on this. I don't want to advertise their names because they're probably publishing, but it's kind of interesting. BU is kind of a hotbed for this sort of thing. And my view is that quantum computers may form this core of the network. So as we looked at in lecture 1 and 2, where the full nodes kind of present the core of the network and manage the blockchain, quantum computers are very likely to perform that function. Wallets will speak into vast farms of quantum computers. And we will have rewritten the blockchain by then, and this won't matter. So good will have won over evil. So there's hope. At the beginning, in lecture 1, I talked about private blockchains, and we didn't focus on them because I think the decentralized trustless model is more interesting, and it will scale from the network effect, so it'll be more ubiquitous. However, in financial services particularly, where I last worked, I sold my company before this one to Bloomberg, and I worked in financial services. And it's a very hard sell to sit down with the Chief Security Information Officer of Citibank and convince him that you're going to run anything on computers that aren't deep in a data center protected by multiple firewalls and all the Bloomberg security apparatus. I couldn't imagine trying to explain to a chief security officer like that we're going to run his application on smart contracts that might run in someone's dorm room in the Ukraine. It wouldn't compute. You'd hear the iPad shutting immediately. So for certain market spaces, private blockchains are just the trick. They want, the customer wants to know that, yeah, we're using blockchain, but it's behind IBM's firewall or it's at Bloomberg. They don't have any blockchain technology to my knowledge yet, but a Bloomberg would be a great trusted partner for this. And building a private ledger among their trading partners would be a great idea behind the firewall at Bloomberg, because Bloomberg has great security experts. So for certain markets, private blockchains actually matter. For others, the public open blockchain, when some of the security issues become more well-known and solved, it won't be an issue. Okay, so in sum, what we've discussed in this lecture is how Bitcoin and Ethereum differ, what smart contracts are, how they work, where they work well, where they work less well. And we've talked about some of the scaling initiatives around Bitcoin and Ethereum and some new exciting services like swapless exchanges. We've posited about where the world might be going with this technology and sort of the impacts of quantum cryptography on blockchain in general. This series, in lecture 1, we went over the components of a network and learned how a blockchain works in general. In lecture 2, we dove a little bit deeper, and in this one, we just covered the smart contract concept. So I've enjoyed very much talking this all through with you. I hope it cast a little light on what blockchain can do and how it might fit into different courses of study or different aspects of the financial system. And please give us feedback on what you learned or didn't learn from this or what you'd like to learn, and we'll take it from there. So thank you very much.